In this video, we are gonna talk about um, basically two things. One is uh, the body wave kernel, but I added one more example that's for a double couple source. So for this particular example, I was using an explosive source, but here I've changed the explosive source to a double couple source, and then I was computing the S sensitivity of the direct arriving S wave. Right, so for the direct arriving S wave, and then this is the sensitivity for the broadband cross correlation delay time. Because it's a double couple source, so the energy um, is not symmetric anymore. The distribution of the energy is not symmetric anymore. So you see this kind of a, if you take a cross section that's kind of in the middle of the source receiver path, you're gonna see the banana donut, but the donut hole is not really. You still see the donut hole, but the sensitivity is not evenly distributed around the donut hole because the energy uh, the energy distribution is uneven from a double couple source. This situation, you don't see this kind of scenario for, don't see this kind of situation for the explosive source, because for the explosive source, energy actually goes, the energy goes going in every direction is about the spatial distribution of the energy is about the same. But for the double couple source, you have a uneven spatial distribution. So this is sort of looking at a plane that's perpendicular to the source receiver plane, and then this is a plane that's kind of in the source receiver plane. So you still see the donut hole in the middle, and then if you compare the source time function used for computing this S sensitivity kernel is kind of identical to this one, but you can sort of see the Fresnel zone. The first Fresnel zone is slightly thinner. Right, it's slightly thinner than the P waves, P sensitivity. Right, that's because the Fresnel zone actually is it's kind of proportional to the square root of the wavelength, and then for the P wavelength is certainly larger than the S wavelength at the same frequencies. Right. So that's why you see a thinner sensitivity for the S wave, S sensitivity kernel, and then you sort of see the color scale for this kernel and this kernel is exactly the same, but you're gonna see stronger sensitivity for the S wave kernel, right? That's because when we compute the sensitivities, the the reference velocity model, the reference the reference S velocity, and also the reference P velocity actually goes into the calculation, right? So in principle, you have to sort of, in order to get the sensitivity, you have to sort of divide some power of the reference velocity, and then the reference velocity of P is certainly larger than the reference velocity of the S. So that's why you see stronger S sensitivity, because um, you are dividing by a smaller number, which is the S velocity, right? So we'll look at this particular example that's from a double couple S velocity, and then um, I'll talk about two programming bugs that actually I discovered today, which actually cost me a significant amount of time to actually track down. I just want to keep a record of it, so in the future I don't make the same kind of mistakes. So let's look at this example first, and then we'll look at the mistakes I made. So this is not on Cheyenne anymore. This is on Mount Moran. That's the small cluster. That's the small cluster at University of Wyoming, and let's look at this the input files for the double couple source, right? So if I go to the forward wave field directory, I now have a new directory that's called 10002, right? And then that's the directory for storing the wave fields from the double couple source. So if I go into that directory, and then let's just take a look at the input file for SW4, right? Everything else is kind of identical. We have this refinement statement, refinement keyword. So the mesh is refined above like 5 km depth, and then P and S velocities, density, and stuff are kind of identical to the previous videos. And then the only thing that's different is this source line, right? And then this source line, you're gonna see some new keywords. So M0, that's the scalar moment. That's 10 to the 15th power. And then you're gonna see strike, dip, and rake, right? So strike. So this is sort of in the Archie-Richards convention. If you have the textbook by Archie and Richards. So strike is sort of the direction of the fault with respect to the north direction. And then the fault is not really vertical, right? It could have a dip, and then for this particular example, the dip is like a 45 degrees. And then the rake is sort of the slip direction with respect to the strike direction. So that's also 45 degrees. So these parameters are kind of a how if you can find the definitions of these parameters in a typical seismology textbook, it's or just the geology textbook, how they actually describe faults, right? And this kind of parameters can be used to describe a purely double couple seismic source, right? So it doesn't have any kind of so isotropic component, right? It's just a purely double couple. And then the source time function is kind of identical to the explosive source. It's an integrated Gaussian, so it's a ramp. And then all the parameters for the Gaussian int is kind of identical to the explosive source also. And then we're recording the velocity field at the receiver location IN-RC01. That's the same receiver location as the explosive source. So when we compute the receiver green tensors, because the receiver is the same, so we don't really have to sort of recompute all the receiver green tensors. So we can just reuse the receiver green tensor we have computed for the explosive source. But one thing that we have to sort of pay attention to is the component, right? So later on, we're going to compute the S sensitivity on the Y component of this particular receiver, right? Don't forget, in the explosive source example, we're using the X component of this particular receiver, right? But now we're using the Y component of this same receiver. So in principle, when we did the explosive source, we didn't actually compute the RGT for the Y component at the receiver. So now we still have to sort of compute the Y component for the receiver. And when we compute the kernels, we don't really have to use all the three components of the RGTs. So what we have to do is to actually compute the forward wave field for this double couple source, right? And then we also have to compute RGT for the Y component of this particular receiver, right? And we're recording the velocity. And then we can just run the forward simulation, and then it's gonna generate all the strand fields, and then the synthetic Southern wave is gonna be like in this particular directory, right? In this particular file. And then if we want to look at it, it's gonna look like let me just load it. Let me see if I got it right. It's one line of code. Yeah, I think that's the right synthetic somewhere. Right. So if you look at the Y scale, so this is the X component synthetic velocity, this is the Y component synthetic velocity, and this is the Z component synthetic velocity. You're gonna see the Y component actually has the largest amplitude. That's 10 to the minus 4, and then the other two components are 10 to the minus 5. Right. So what I did was to actually use this particular S wave. Right. I'm using this particular S wave. Right. If you look at the X component, you see this particular phase. Right. This particular phase doesn't look like a it's actually a composition of two waves. One is the direct S, and then there's also a PP, surface reflected P. They are arriving at about the same time, and then because they have a finite duration, so they interfere with each other, producing this kind of a waveform. Right. On this component, on this Y component, you're gonna see a S wave. a very strong S wave, basically a very strong S wave. So all we have to do is to actually take out this component, right, and then convolve it with the source time function used for computing the RGT, right? And in fact, the source time function for computing the RGT was actually identical to the one that we used for the explosive source example. So now we have to compute the RGT for INRC01.y. So for the explosive source example, I only computed the one for the x component. But now we have to compute the strain fields for the y component. So if I go into this particular directory, right, and then look at the input file for SW4, it's pretty much identical to the input file for the x component, right? And then the only thing that's kind of different is this body force. So for the x component, fx equals to 1, fy equals to 0. Now for the y component, fy equals to 1 and fx equals to 0. Right? Everything else is kind of identical. And then the source time function is still the low pass filter, the Butterworth low pass filter, filter with a corner at 2 Hz. It's the same thing, right? And then if we sort of compute this strain fields, it's going to produce g1.dat, right? That's the source time function that's resampled to the time steps, to the time samples used for the SW4 simulation. And then all we have to do is to actually convolve this file with this subram, and then pick the window, pick the time window after we've done the convolution, and then all we have to do is to actually call WPK, right? So all we have to do is to go back to jobs, and then WPK, right? So it's gonna read the wing list file. The wing list file, if we look at the wing list, it's got 3 windows now. So this was the explosive source window. This was the surface wave example that we did using the same structure model. And then this new line was added for our double couple source, right? And then that's the window file, right? If we want to look at the content of this particular window file, it's just got a one window that starts from 8.5 seconds, and then ends with about 12 seconds, right? This is already accounted for the non-zero phase shift of the low pass filter of the Butterworth low pass filter. So and then we are computing. So this flag is the WPK type flag. We're computing the WPK for the broadband cross correlation delay time, right? So and then this is actually the component ID, right? Because it's not on the X component, right? So for the explosive source, this number was 0, right? Because it's on the X component. But now it's on the Y component. The Y component has an ID of 1, right? So 1. And then all we have to do is to call WPK, right? And then we can just call WPK to create all the WPK files. And then once the WPK files are created, we have to create the kernel directory, right? So now we have to create a new kernel directory for the double couple source, right? And then underneath the double couple source, that's the receiver and the component, right? And then underneath the receiver component, that's gonna store all the kernel files, right? All the kernel files. Right. So all those kernel files were created by calling dsk, basically. Right. So if we look at the run dsk.sh, it's going to use this wpk lst file. So wpk lst, it's got like one more wpk file. That's this line, right? And this line, if we look at it, it's actually a link. It's actually a soft link. Right, it's actually a soft link inside of the KER directory, and then it's pointing to the WPK file that's generated inside of the forward wave field for the double couple source. Right, and this soft link can be created by either manually or just by using a script. Right? If you have lots of these kind of WPK files that you have to link, it might be better to just create a Python script or something, and then just use that script to create all those links automatically. Yeah, that's the input files for the DSK code, and then all we have to do is to run the DSK code, and then it's gonna create all those KV files, right? And then once all the KV files are created, what we want to do is to actually extract the cross sections. What we have to do is to extract the cross sections to make a plot, and the cross sections are specified by KV_XSC file, right? So if we look at this particular file, where is that? KV_XSC, right? If we look, it's got like two cross sections. So we are looking at so 0 means P kernel, right? 1 means S kernel, S sensitivity. Right? And then we have only one window, so only one WPK, right? It's not frequency dependent, so it's broadband cross correlation. So it's just one window, one WPK. So 0 is WPK, and then one cross section is set at y equals to 38, and one cross section is set at x equals to 88. Again, these numbers are after grid decimation. So you have to sort of do some kind of simple calculation to actually get the total number of grid points after the decimation, and then account for the locations of the source and receiver, and then try to pick the correct position or the coordinates for the cross sections, right? And then all we have to do is to call avk, right? Call avk. So avk.sh, right? I had this avk call for the explosive source example, and then had this avk call for the surface wave example, and then this line was added for the double couple source, right? And then after I finished calling avk, I was sort of transferring all the ASCII output files to my local machine to use MATLAB to make a plot. Right. So now the MATLAB script for plot kernel body waves has been added to plot the S kernel. To plot the S kernel for the double couple source. So these two cells are kind of added to plot the S kernel, and then once you have finished running this particular script, it's going to create this kind of file. Right. Again, it's not organized in any way, so it's kind of distributed everywhere. Right, but that's probably sufficient for validation purposes. Right. Okay, so that's the double couple. That's the S sensitivity for a double couple source from a double couple source, right? Now let's look at the two bugs I discovered today. Both of them actually. So one of them is because of my carelessness, and the other one is because of my lack of knowledge about C++. So one of the problem, the first problem, which probably easier to sort of discover, was uninitialized private data members, right? Uninitialized private data members, and those uninitialized data members were in the IMV object or IMV class. These data members, the IMV class is responsible for reading the inversion control file. That's the IMV. That's this particular text file that controls all the different parameters for the inversion process, right? And this IMV object or IMA class is used almost everywhere throughout all the codes, right? And all the inversion codes has to query this particular IMV object in order to actually retrieve, for example, the model path, and then the kernel flags, and then the grid decimation rate, that kind of thing, that kind of information, right? But I forgot to actually initialize some of those private data members, right? And so depending upon how the user is gonna construct this particular text file, right? For example, in this particular text file, I did not actually specify the parameter IT shift. So you don't see a parameter called IT shift in this particular text file, right? And this IT shift was actually used to account for the shifting of the Green's tensor or RGD Green's tensor. It's a parameter that I used before to actually try to make sure that the RGTs and the forward wave fields has the phase that's aligned correctly. So in order to actually produce the donut hole in the body wave kernel, in the director P wave kernels, right? But I've stopped using that. So the current version of the code doesn't actually use IT shift anymore, right? So in this particular text file, you don't see a value for IT shift. So IT shift was left uninitialized, right? So here this code is initialized, right? It has been initialized to 0 together with all the other sort of parameters, right? But but before I discovered this problem, this parameter was left, this private data member was left uninitialized. And then depending upon the machine that I'm running on, for example, if I run on Cheyenne, it looks like that environment is going to automatically sort of initialize or provide a value for those uninitialized private data members, right? And that value happens to be 0. But on Mount Marion, there's the initialization value was like a completely random, huge integer, right? So, and then in my kernel code, at some of the locations, IT shift was still used to shift the temporal indexes, right? So that created a huge problem for me when I run it on Mount Marion, and I spent lots of time trying to discover where the problem actually is, right? I thought it was just a so the error message I see was a segmentation fault, right? So segmentation fault usually happens when you access array out of the bounds, right? So the index of the array you're accessing is out of bounds, right? So I was kind of trying to find all the look into every array or every index, try to actually count what's actually the maximum index, right? And I use different kind of debugging tools. It turns out the IT shift was initialized to a huge number. So all my temporal index were kind of pointing out of the array, right? Pointing out of the array. And then for some reason, either the compiler or the debugger or the maybe I did not specify the correct flag on the compiler, right? Usually this kind of access out of bounds can be specified, can be detected by specifying some kind of compiler flag, right? I was using GNU G++ as a compiler, and I forgot what's actually the flag for detecting out of bounds access. Right. That was the first problem that I had. Uninitialized private data members, so don't forget to do that in the future. I'm talking to my future self. Don't forget to do that. Basically, initialize every private data member. And then a second problem I had is related to a particularly interesting feature of C++. So here I have constructed a very simple example. It's related to the C++ vector container, right? It's so here I have a three-dimensional vector. It's a cube, right? It's a cube of doubles, right? And what I wanted to do is to actually sort of change the size of this three-dimensional vector depending upon some of the parameters I specified at the beginning. So here so the three-dimensional vector is called a W, right? And then here I do a clear, right? And then do a resize. So when I called the constructor, I didn't actually specify the dimension of the three-dimensional vector. So, but when I do a resize, I can actually use those numbers to actually specify the dimensions, the size, of the three-dimensional vector in each of the dimensions, basically. Right. And then here I'm actually printing out the size of each dimension. Right. And then I changed one of the parameters NWPK from 3 to 1. And then I did a clear, and then I do another resize. So after this resize, the second dimension of, so the first dimension is nk, right? Nk. The first dimension is nk. Nk equals to 2 for both cases. I didn't change nk. But the second dimension, nwpk, so for this resize was it's the second dimension is supposed to be 3, right? And then afterwards I changed the nwpk to 1, and then I did a resize again. And so it's supposed to be 1, right? And then here I'm printing out the size of each dimension. Right? The error I made was that I forgot to do the clear. So if I forget to do the clear, let me just comment out this clear, and then recompile it, and then call this code. You can sort of see the second dimension didn't change. The second dimension didn't change at all. It's supposed to change from 3 to 1, right? But it's still 3. It's still 3. Right? It's not changing. So I have to call clear first, and then it's gonna give me the correct behavior. It's changing. It's reducing from 3 to 1, right? And this kind of problem happens. If I forgot to call the clear first, the resize is not going to reduce the dimension, right? But suppose I change NWPK to like a fourth, right? And then I still sort of forget to do the clear, right? But it's still not changing. It's not increasing. So in order to actually change the size of any dimension, I have to actually call the clear first, right? Otherwise, C++ is not gonna actually do the resize. So now it's 4, changing from 3 to 4, right? And this is another problem that consumed a significant amount of my time to actually track down, right? Because I thought that resize is going to change the dimension for me, and then my code is actually, when I access the three-dimensional array, my loop indexes are actually sort of determined based upon those changed numbers, right? So that's going to give me out of bounds access. If the three-dimensional vector is not really changing its size, then my loop index is going to access out of bounds. Is going to access the array out of bounds, right? That's going to give me segmentation mode, right? So this w.clear, this clear call is kind of crucial in order for the resize to actually take effect. And I honestly did not know that before today, right? This is a feature of C++ that I'm not familiar with. Maybe I know that a long time ago, but I forgot, and I forgot to document it. So I have to relearn it, and it's very time consuming to track down those bugs. Okay, so that's it for today.